So you might have noticed that some things seem very familiar from what we've done last week. The problems that we've solved so far this week look a lot like the problems that we solved last week. And some of the equations that we're seeing this week look a little bit like the equations we saw last week. Last week we were talking about work, and we used work to calculate a lot of things in our sample problems. And this week we're using potential energy to calculate a lot of the same types of things. You might also recognize the similarities between some of the equations from last week and this week. So for example, last week we calculate how much work different forces did in different situations. And we found that whenever we were talking about gravity, it was really easy to calculate how much work gravity did. All we needed to do was do m times g times delta y, where delta y is the change in the y position of our object. And we said that that's how much work gravity did, because gravity is always exerting a force of m times g. And to figure out work, we just did the force times the distance the object moved, which for the case of something moving vertically, and when you want to calculate the force of gravity, all we really care about is how did the object's y position change. We had to add in the positive or negative here, because if delta y was positive, that would mean the object moved upwards. We wanted to indicate that gravity did negative work. So we always put this positive or negative in here, where you would have to decide, did gravity do positive or negative work based on, how the object was moving. So this formula is not coincidentally identical to the formula for the change in the gravitational potential energy of an object. Now this might look a little bit weird here with a delta U and a delta Y. I don't want you to see a delta symbol and think that you don't know what's going on. Very often when we see a symbol that we're not that used to, like this delta, it makes us think we don't know what this is, and it makes your brain turn off, and then you just don't pay attention and you don't learn anything. So let me just remind you, this delta is not something crazy. It just means final minus initial. So let's just focus on this equation and be very clear that we know what's happening with this equation here. So let's just take a minute to go, let me think about that. What does delta U mean? It means take the final potential energy due to gravity minus your initial potential energy due to gravity. That's what delta means. Well, what is my final potential energy due to gravity? It's just equal to mg times y final, where y final is your final y position. It's the position of your object, the y position of your object at that final event. And your initial potential energy due to gravity is just equal to mg times y initial. So I could factor out, from this expression here, factor out the mg, and you're left with mg times y final minus y initial, and y final minus y initial is just the same as delta y. So that's why I can write this delta U is equal to mg delta y. Okay. Now these two things are the same, except they're going to be off by a negative sign. So what we can conclude from this is that the work done by gravity is always, always, always equal to negative of the change in the potential energy due to gravity. And that is not a coincidence. That's how we define what potential energy means. Okay, so for a force like gravity, when gravity does positive work, that means that the potential energy has decreased. Think about that for a second. Does that make sense? When gravity does positive work, it means the potential energy of that object has decreased. So if gravity does positive work, that means the object moves lower. And if the object moves lower, that means that the potential energy is decreased, or delta U is a negative number. Okay. Now I'm not going to go through the derivation, but if you remember what we do with springs, whenever we had to calculate the work done by a spring, we had to integrate, because the force of the spring depends on the position, and as we move different positions, the force changes, so we need to integrate. And we were integrating an expression that looked like kx. When you integrate that, you get 1/2 kx squared, which was the potential, our formula that we've just seen today for our potential energy stored in a spring. So it is also true for a spring that the work done by a spring is equal to negative of the change in the potential energy of a spring. So these are not coincidences. These are this is just another relationship that helps us understand what potential energy means. When the spring force does positive work, the potential energy of the system decreases. Okay. So one way we can think about this is that when we use the change in potential energy, when we use delta U, it's a shortcut to calculate how much work these forces are doing, okay? Calculating how much work gravity does is easy. It's just like calculating how the potential energy of the system changes due to gravity. But calculating how much work the spring force does is not easy. We have to integrate. But now that we know that the work done by the spring force is the same as the change in potential energy due to the spring force, and my formula for the potential energy of a spring force is simple, 1/2 kx squared, this gives us, using potential energy, gives us an easier way to calculate how much work the spring did. So I think that it's always easier to use potential energy than it is it's always easier to use potential energy than it is to calculate how much work the spring is doing. So this is kind of like a little shortcut. So let's bring this back to what we did last week. Last week we used the work energy theorem to calculate how the kinetic energy of an object changes. And we calculated the net work. So we looked at all the different forces acting on our object, and we figured out how much work each of those forces did, and then we added up all that work to figure out the net force. Now what we can kind of do is kind of make sense of what we've been saying so far this week, which is talking about how mechanical energy is conserved if we're just dealing with gravity or if we're just dealing with the spring force. So if gravity or the spring force are the only forces that do work, okay, then, meaning if there's no other forces doing work, then instead of talking about the net work, what I could do is just write in here, this is the change, negative of the change in potential energy. Why is that? Because, so this would be like the work done by gravity. Well, the work done by gravity is negative delta U of gravity. Or if this is the work done by the spring force, that would be negative, this work is equal to negative delta U of the spring force. So when I write it like this is kind of like the total change of potential energy. Maybe the gravitational potential energy is changing, maybe the elastic potential energy is changing, or maybe they both are changing. But this expression just represents the total change in potential energy. And if nothing else is doing work, then the net work done on the object is the total change in potential energy of our system, a negative of that. And now if we look at this expression, well, what is delta U? That's U final minus U initial. What's delta K? K final minus K initial. Okay, so here I've just plugged in delta U I've plugged in saying it's U final minus U initial. And this expression now I can rearrange to put all the initials on the same side and all the finals on the same side. And here is our conservation of energy equation that we've been using. So what can we say? If the only forces that do work are gravity and the spring force, then this will be our result, and mechanical energy is conserved. Let me just say that one more time. If the only forces that do work on our system are gravity and the spring force, then mechanical energy is conserved, and I can use this expression. We'll talk later about, well, what happens if there's another force doing work. We'll talk about that later. So let's look at this example. Press pause, think about it, and try to give me an answer. Okay, so now in this case, when we have objects sliding down these different slides, or ramps, whatever they are, there's no friction, okay? The normal force in this case is not doing any work. The normal force is not doing any work because the normal force is always going to be acting perpendicular to the direction the object is sliding. So the normal force doesn't do any work. So the only force that is doing work in this example is gravity. And because the only force that's doing work is gravity, I know that mechanical energy is going to be conserved. I know that Ki plus Ui up here has to equal Kf plus Uf down here. And all of these are the same height. So the initial potential energy, Ui, is the same for all of them. They all reach the same height at the bottom, so U final is the same for all of them. That means that K final is the same for all of them, and the speed is the same for all of them. Okay, so these objects are not in free fall, but it still is true that Ki plus Ui equals Kf plus Uf, and it's true in this case because no other forces are doing work except gravity.